Okay, try to solve sine x is equal to x. I dare you. Solve it. Go on. Finding it very hard? Yes, that's because it's very, very difficult. Okay, now we have not got ways to work this out at the moment. So sine of x is equal to x can't be solved. Okay, using our traditional methods. What can we do? Well, we can't factorise, we can't set it equal to 0, and so it's not a polynomial. What can we do? So what we're going to do is use two different methods. The first one was what we call halving the interval. So we could draw a graph up and have a look and estimate it. It's not going to be great, but these are what we call iteration methods, and the idea is to keep repeating the same process until your accuracy gets better and better. Now, these methods work very nicely for with a computer, because computers will do lots and lots of simple tasks very quickly, because they're morons. They don't question it. Okay, but what we want you to do is be able to program a computer in that regard and be able to apply the method to actually do this. So we won't ask you to do it as many times as a computer. What we want to do is consider where a curve will cross an x-axis. Where has it got a root? So if that's the case, we have a look at this idea. If we look at x1 and x2, if we take the function of x1, we would see that would give us a negative value. If we take the function of x2, we see it's got a positive value. So what we would say there is that there must be a root between x1 and x2. So if that's the case, that there's a root between x1 and x2, what we want to do is narrow the values of x1 and x2 as such till we get closer and closer to where the point is. So, but if we want to prove that a root lies between 2 points, just show that they've got a sign opposite, and then you're able to do that. So what we want to do is work on the idea that we can get these 2 points and then take the midpoint. Say x3 was the midpoint there. So we'd find the midpoint and then test the midpoint there, fx3. Now the idea here is that if you're going to get one of three situations. So we've already shown that function of x1 wasn't 0, it was negative. Function of x2 was positive. So if we take the function of x3 and we get 0, bingo, we've hit the required root. So it must go through the x-axis. Only unlikely it's going to happen. Function of x3 though, if it's less than 0, that means that x3 is still negative, which means you've got a situation there where we've picked x1 and x2, and we've got the midpoint, and the midpoint is still negative, which means the root must lie between the new point x3 and that point x2, and that's what it means there. So if it's negative, basically it replaces the x1 value as the one where it's going to be negative. So basically what we've done, we've halved the interval. That was the interval it was in. So between x1 and x2 is where the interval was. But now because we've taken a point in the middle and we found, well, the curve now crosses between that point and x2, we've halved the space that the curve was existing in from before. So we've halved that interval. If, on the other hand, we get the function of x3 being greater than 0, then that root must lie between x3 and x1. So it means it's on the positive side. So the root now lies between those 2 points. So, and it replaces the x2. Again, we've halved the interval there. So what we do is then keep repeating those processes. So we take the interval, whichever interval we have, we halve that again. We take the midpoint of that one again, and then find a value x4. Find if it's positive or negative, and then see which half of that interval between x1 and x3, or x2 and x3, is where we're going to take. Which side of x4 is the root going to lie? And you keep doing that until you get a required accuracy, whatever decimal point you're looking for. So that's the idea of halving the interval method. So let's have a look and see how it works. So you show that the polynomial here has a root between 0 and 1. Well, when we put 0 in, we get a negative value. When we get 1 in, we get a positive value. So yeah, there must be a root between 0 and 1 there. It must lie somewhere between those two. So the next one, we want to halve the interval twice. So we take the midpoint of 0 and 1, which is half, sub that in, we get it being negative. So that means then that we had the root at 0 being negative. So when we take a half, it's still negative. So that's when we take the half value there, it's still negative. So it must lie between a half and 1. We apply it again, so we get the midpoint of a half and 1, which is 0.75. Sub that in, we get it being greater than 0, which means that when we take the 0.75 there, so the 3/4, it means that's positive. So it must lie between a half and 3/4. So we've narrowed our distance. We're starting to get to 2 decimal accuracy in that regard of how small our interval is. And we can just keep doing that. You can see how a computer is going to work that and keep doing it over and over and over again. You can program the computer to do it until you get to a total, like a huge amount of decimal places accuracy. Again, depends on if it's an irrational root, it's not going to give an exact value with a decimal approximation. For part C then, we're going, well, which of the x values in part B is close to the root? Justify your answer. So again, we'll halve that interval. We halve the interval between 0.75 and 0.5 and 0.75. And so we get 0.625, sub it in, we get a negative value. That means the root lies between 0.625 and 0.75, which means it's closer to 0.75 than it was to 0.5. So you can see here, like that was a net positive there, negative here, positive there, and we test in the middle, it becomes a negative value, which means the root must be over this way, which is in this half, not that half, so it's closer to 0.75 or 3/4. Let's have a look at this one. Like, you're not going to be able to solve that one with an x squared and a log of x plus 3 in it. So it's got a root close to 1. So show the root lies between 1 and 1.2. So we sub those values in. We see that we get a negative value and a positive value. So it must lie between those. So by using the halving interval, we'll find the closest value of the root. So we look at 1.1 and we get that that's negative, which means it's going to replace the 1 value, which means if root's between 1.1 and 1.2, so we make an estimation and say, look, out of 1 and 1.2, 1.2 is the closest to the root as the root lies there because it got replaced there. So that's what we'd say about finding the closest value of the root. So we're getting down 1.1 of a decimal answer accuracy. So in this one, we've got a cubic and it has only one real root. So show the root lies between 0 and 2. So there we go. So that we can get a negative value, then a positive value. The root lies between there. As long as it changes sign, we know the root lies there. We halve the interval, so we'll take the function of 1. So, and we get it positive. So it's going to replace the value of 2. So the root lies in the interval between 0 and 1. So it lies on that half. Then, and then by which end of the small interval is close to the root? Again, briefly justify your answer. Well, again, let's take the half of that interval. So, and that's going to be less than 0. We get put on a half. It's less than 0. So the root lies between 0.5 and 1. So the root was closer to 1 than it was to 0. And that's how we start to work this method. We start to be able to put in values and keep halving that interval till we get the accuracy we want. X cubed minus natural log of x plus 1, the root between 0.5 and 1. So show the root lies between 0.8 and 0.9. So we, again, sub those in. We get one of them being negative, the other one being positive. So it must be, root must lie there. Halve the interval, and to get the value of the root, correct to 1 decimal place. So we put the 0.85 in, which is halfway between 0.8 and 0.9. It's negative, which means the root lies somewhere in this interval between 0.85 and 0.9, which means to 1 decimal place, well, anything there when we round it to 1 decimal place would go to 0.9. So that's why we would say to 1 decimal place, it would be equal to 0.9. So we can do this to any accuracy we like. If we wanted 2 decimal places accuracy, we could halve 0.85 and 0.9 and get it closest to either one of those. So we can keep repeating and see where, as I said, as a computer would do this very well. But that's how we do this method. Halving the interval. Keep halving our intervals. How many times we're told to do it to get a decimal that is in accuracy of whatever we need or we're told to find.